So I'm deeply honored to have former Minister Champika Ranawaka chairing this session. And in particular, I have tailored my talk towards energy simply because it is so important in our lives. Now, as introduced by Vidya, nanotechnology can be used in all forms of everyday activity that include some of the clothing industries that were talked about, includes the semiconductor industry, includes the lighting technologies. Industry 4.0 is based on all sensors and AI that is controlled effectively by the inputs coming from nanotechnology. Now, all of these are important, but what I want to highlight in this particular talk is the importance to energy. And this is even more critical from a country such as ours that spends so much of our resource in this area. And I hope that many of the engineers and scientists who are involved in listening to this talk will be empowered to contribute to the activities of the country going forward. I would also like to have a subtext to my talk, which is building stronger and smarter post-COVID, simply because to acknowledge the fact that we are all living in very difficult times, strange times. It also means all of us have to make some sacrifices in our lifestyle. But what I hope is that by using the provisions enabled to us through technology and science, we can build stronger. Before I go into my talk, I'd like to thank the members of my group in particular, and James, Imaka, Shashini, Hashini, Ravi, and Kea for some of the slides that I will be using within my presentation. A brief introduction to where I come from and the work that I'll be presenting and how I've got to this point. The building that you see in the background here in blue is the Advanced Technology Institute at the University of Surrey. And we've got about 150 researchers working on different forms of advanced technologies and embedding nanotechnology within their activities. Some of these range from water filters, for which we have got a national award, Queen's Anniversary Award in some of the activities. I'm part of the electronic engineering department where we design and fabricate satellites. So we are one of the few universities in the world to make satellites all the way from cradle to grave, really, in terms of not just building satellites component by component, but also removing debris in space. So once more, if people are interested, you can see Remove Debris program that we started with ESA that shows how we can remove these particulates and satellites from space. The work within my institute was recognized by the Majesty the Queen some time back in getting a Queen's Anniversary Award. And the image that you see at the bottom left hand is from the Winter Olympics, the last Winter Olympics. And the reason I put that image up is that that's the Hyundai Pavilion at the Winter Olympics in South Korea. What is significant about this is this was highlighted as the darkest building on Earth. Now, what is important about that is that this dark color that you see is all based on carbon nanotubes. Those carbon nanotubes came from our lab. It's a spin-out company called Surrey Nanosystems. And what it emphasizes is, in the case of nanotechnology, you're dealing with particulates that are on the micron and nanoscale. But it can have impact on materials, systems, buildings that are much larger. So the importance of nanotechnology here really is on the design aspects. And by designing properly, you will be able to have those effects on much larger areas. And although the Hyundai Pavilion that was put up was associated with a showcase, so that even in the dark nights at the Winter Olympics, it stood out as a building, it has implications associated with some of the motor vehicle parts that are coming out of the car industry at present. It's used in satellites for imaging because it has the most absorptive properties available to mankind. Now, I'd like to take you back 18 months or 20 months and just put a context to my talk. Just imagine Piccadilly Circus in London, one of the most vibrant cities, one of the cities with the largest population, ethnic diversity, enjoying the day. Overnight, this Piccadilly Circus ended up looking like this. Heathrow, one of the busiest airports, or one of the 3 busiest airports in the world, moved from this particular situation to this. And places of learning, such as Cambridge, ended up having quadrangles that had no one there. King's Parade, no one there. Now, this is the impact of COVID within the UK. And I'm sure in Sri Lanka and the rest of the world, we've all seen this impact. We all have an obligation to work together to get out of this impact. And the reason why this is important is this is not just related to one aspect, but many aspects. The grim reality is that many of these aspects that have come with this sort of impact started with the use of fossil fuels. And with the use of fossil fuels, although it's something that has been absolutely paramount and significant to development, it meant that the temperature that was stable over 10,000 years suddenly became unstable. So within the geology terms, you talk about periods, epochs in time. And this is the Holocene period where there was no variation in the temperature beyond the plus or minus 0.4 degrees. The insatiable appetite for energy and quality of life and development has ended up creating islands of plastic waste. And these clearly are important in certain aspects, but we've seen why we need to get rid of this simply because we cannot continue to pollute the world in the name of development and enjoy the benefits while somewhere else your problems start piling up. And we really have made a significant change when we look at the history of mankind and say in 2.5 billion years, we are the first race that has managed to change the course of the world, because we've created what we call the Anthropocene age that has come after the Holocene age, where now, if we were to dig a hole to this current time, you will see more man-made objects, more Anthropocene type objects than natural objects. So we really have made our mark here, and probably made our mark in the wrong way. Now, clearly there have been very positive things with the unparalleled growth of quality of life and wealth creation, but maybe in a sense there is some sort of payback now coming because the earth needs to have sustainability contained within its own activities. There are also sometimes pauses that you can have in terms of what you see and think maybe the current COVID crisis is a time to rethink our strategy going forward. And this is basically showing what happened in satellite imagery of gases coming out of China between January and February 2020. And what you immediately see is a huge drop in NOx or greenhouse gases in comparison from one month to the other, indicating maybe it is showing us a way that we need to slow down in certain areas if we want to keep our planet clean. So the post-world COVID that we need to think about going forward, and particularly with engineers and professionals there to build it is going to be different. We need to rethink what our priorities are going to be. We need to be able to understand and engineer things going forward. The whole idea of megacities, the whole idea of developed technology that is working closely with buildings, with your transportation sector, with recreation, etc., are working together in a cohesive manner in such a way there is connectivity and information exchange. We need to start thinking of smarter ways of doing things. We need to start using supply chains. And one of the great things about nanotechnology is that you can make more efficient products with less material, more robust products, but reduce the cost and reduce the waste associated with it. All of this can come with Industry 4.0. So new innovation can come in the post-COVID world. And if we do not actually change our ways, there is a stark warning here given by the Chancellor of the Bank of England. The former Chancellor of the Bank of England, Mark Carney, indicated that a climate crisis would create significantly more deaths than the current COVID crisis we are facing. So it's a wake-up call to all of us that we have taken the earth for granted, and now we need to start thinking about ways in which to build back smarter, a better world using science and technology. Now, moving on to the main theme of my talk, which is about energy. If we start looking at the energy mix currently being used, and typically the US energy mix is very much mirrors the world energy mix when it comes to round figures. And if we look at where the energy mix was 10 years ago, typically 80% of your energy came from coal, oil, and gas, so fossil fuels. Renewable energy accounted for around 10%, nuclear about 10%. And this was at the time when Barack Obama was the president of the United States, and he had signed up to COP21, the Paris Agreement, in order to reduce greenhouse gases, etc. If we look at what happened roughly 8 years afterwards, the United States is still using nearly 80% of fossil fuels, roughly 10% of renewable energy, and 10% of nuclear. Things have not changed hugely, despite us knowing there is a huge climate crisis looming up. If we were to look at the world energy balance, again, this is an editorial that I've just written a couple of months ago to the magazine Energy and Environmental Materials. Fossil fuels make up nearly 80% of all of the world energy use currently. From a world point of view, nuclear accounts for about 5%, and renewable sources account for about 15%, with solar and wind amounting to just under 2%. So that's a world energy balance. The problem we have here is that despite knowing there are climate change obligations that we have since Kyoto in '97, we still have 80% of all our energy coming from fossil fuels alone. Now, is this sustainable? If we look at the last complete year that was not affected by COVID, and we look at the CO2 emissions, in 2018, 37.1 billion tons of CO2 was emitted globally. And as you can see in the graph on the left-hand side here, is that the total emissions in the world keeps going up. You can see that the main culprits associated are the US, the EU, and China, and India. with the rest contributing what is shown here. But we cannot continue to increase the CO2 emissions at present and leave it for the world to be a sustainable place. If we look at the correlation of the CO2 emission that you see here in blue and the temperature rise that you see in red, what you see is this correlation that beyond the 320 parts per million of CO2, there has been a relative rise that is proportional effectively between the temperature and CO2 levels. Now, one would say maybe that's associated with the data set I've used, but this data set can go up to many hundreds and thousands of years, and it will have the same sort of position. We also know at the present time, the increase in temperature is at around 1.2%, 1.2 degrees. And we cannot afford to allow this temperature to go beyond the 1.5 because there will be catastrophic effects coming into play. And these could be anything from your storms, from global warming issues with the melting of the Arctic. You could have snowstorms coming in Mexico, and these sort of weather events that are completely out of the ordinary. In fact, I will show a clip of some of those weather events when I come to that and discuss that point. Now, the solution that has been proposed is that we need to go to a net zero position. What I mean by net zero is that we need to be able to balance out the anthropogenic greenhouse gas emissions with the anthropogenic removals. Typically at the present time, there is about 20 gigatons of anthropogenic removals coming through forests, bogs, marshlands, etc. But our emissions are at around 37 gigatons. So we need to drop this from 37 all the way down to about 15 to 17 in order to have a balanced activity. And if we can keep that balanced activity, that means that we will have a net carbon emission position. If we cannot do this science-based reduction in the CO2 emissions that is now being proposed through IPCC, the problems are quite severe. So for example, if we miss our 1.5 degrees by 2050 to say 2 degrees, the predictions at present are that there will be over 11 million people exposed to extreme heat, 60 million people or more exposed to drought, 10 million more people exposed to rising sea levels. And these are just a few of the potential crises that are going to hit humankind as a result of global change, climate change. And these temperature rises will have catastrophic effects associated with flooding, precipitation, desertification, acid rain, biodiversity loss, etc. Now, this sort of movement of people and changes in climate certainly give rise to major events, extreme events, and in some cases, the spread of diseases like that we are seeing at present. If we were to look at the impact of climate change,
it's the general scientific consensus that climate change is causing an increase in extreme weather events around the world.
Oh my God.
From sea level rises to droughts, extreme weather can seriously cripple affected communities. But what is considered an extreme weather event? Extreme weather can be very dramatic, with fire tornadoes, wildfires, severe tropical storms, hurricanes, and cyclones being the prime examples. According to the Intergovernmental Panel on Climate Change, an extreme weather event is an occurrence that is more severe than the historical norm. They point out that even statistically, non-extreme weather events can cause significant damage to economies, societies, ecosystems, and infrastructure. As of 2012, there have been more than 800 major extreme weather events recorded worldwide, causing hundreds of billions of dollars in damage. Other sources, like the UK Met Office, show a marked increase in extreme events, which caused loss from just over 200 in 1980 to over 700 in 2015.
So what is very important to note here is that within the first 9 months, within the US, there have been more extreme events than the whole decade. Worldwide, there have been more extreme events this year than the last 10 years. So these events are happening more and more frequently. And much of this could be associated directly to the CO2 emission that is creating the increase in temperature. Now, the question to ask is there a solution to this problem? Now, looking at it holistically, we can ask also, what sustains life on Earth? If we look at the fundamental question as to what sustains life on Earth, it is energy, and it's energy from the sun. The sun not only gives us the abilities to grow our crops and to be able to farm, but it also, in the past, through fossilization of vegetation, etc., given rise to coal, petroleum, and gas. The problem we currently have is that when we use fossil fuels, you have removed a densification of carbon capture that has happened over millions of years and released all of that in one go to the atmosphere. So if we want to have a sustainable lifestyle, we need to rethink of how we do things. And we can continue to farm, we can continue to grow things, but we need to start looking at ways in which to directly use the energy that is given by the sun to the earth. Now, one could say, is this feasible? Is this possible within the current economic envelopes that we all find ourselves working in? Furthermore, if we can start using direct conversion of solar energy to electricity, it actually allows us to tackle a number of major problems. If we look at the typical energy mix associated with the users of energy from a national context or a world context, about a third of your energy is typically used for household use, domestic use. About a third of it is used for industrial use, and about a third of it is used in the transportation sector. We know that from a household point of view, in most cases, the electricity can certainly supply the energy needs there. At the moment within the UK, one of the major areas of change is the gas boiler, as to whether the gas boiler can be removed and replaced with ground source heating and electrical fans to move the air around. In the case of industry, there's no question, electricity can be the main form of energy. And in the transportation sector, as you have seen, many countries have now declared that beyond 2030 and 2035, there will not be only petrol or only diesel cars, but there will be hybrid vehicles and in particular electric vehicles coming in. So electricity really is one of the most flexible forms of energy. And the question is, if we can convert that energy from the sun through windmills or solar farms into electricity, that would certainly be helpful. Now, if you look at the amount of energy that is coming from the sun and do a very simple back of the envelope calculation to see whether the potential is there for there to be enough energy to be captured, what we find is very surprising. If you use Planck's blackbody radiation law, you can show that the total energy flux coming in is something called the Stefan Boltzmann's constant times T to the 4. And that total amount of energy that comes from the sun to the earth is around 175,000 terawatts of energy. Now, the world as a total at present uses around 15 terawatts of energy. And this world energy use is not just electricity, it's total energy use that includes the transportation, includes domestic and industry. So what is immediately apparent here is that the sun delivers to the earth over 10,000 times more energy than we use. So maybe as an engineer, something that one could think is, isn't it time we try to use even a fraction of this energy and power things? If we were to look at it graphically, the big yellow box is the total amount of energy that irradiates the earth from the sun. These various boxes inside contain the total capacity of wind in purple, biogas, biomass in green, and geothermal. And this orange box in front is basically the total energy expected to be used by 2050. So it represents 50 terawatts of energy. So what this is basically saying is, from a potential and capacity point of view, there is certainly enough energy that hits the earth that can be utilized. In terms of the economic equation, what I show here is the comparison of the different renewable energies that are most popular with the different fossil fuel energies. So what you see in this light green band are the fossil fuel cost range. So the cost range for fossil fuels from a worldwide perspective is between 5 cents per kilowatt hour to around 17 cents per kilowatt hour. That would equate to about $50 per megawatt hour to $170 per megawatt. What we see within these graphs is, within the last 10 years, the onshore wind price has kept coming down and down and down to the point where it's now pretty much close to the lowest cost you would pay for fossil fuel. Solar energy, once more, solar PV, started high 10 years ago. It's come crashing down to the point now, and in this case, it's 2019, and I'll show you the current data in the next slide. It's comparable to the lowest cost. So no longer can we say there is a cost argument that fossil fuels should be retained. And that's something I'm very happy to take a challenge on, and we can go back and look at those numbers from a worldwide scale, whether that's correct or not. Now, this was what I did in this editorial that I wrote for Energy and Environmental Materials, where I plotted out in the last 10 years, what is the average cost people have paid for energy. If I take nuclear energy, that's shown in blue here, that's at around 170, 180 per megawatt hour. If I take coal, that's probably around 120. If I take a combined gas, systems, we're talking about 40. If I take wind and solar, it's coming below 30 at present. And this is not the end of these, because the predictions at the moment show that there may be some plateauing, but I don't believe that is the case, as I'll show you in the analysis that follows. In my view, I believe that the energy cost associated with solar will probably drop to less than $10 per megawatt hour. In fact, last month, a power purchase agreement in Saudi Arabia sold it at 1 cent per kilowatt hour. And that's for over 200 megawatts of energy. If we say hydrogen is the future, if I can use energy, electricity from my solar system to run an electrolyzer, I can now produce a kilogram of hydrogen at 1.6 US dollars per kilogram. And once more, hydrogen, which was thought to be too expensive really to power networks, despite giving very clean energy, becomes feasible. So this is all possible with silicon. This is all possible by looking at silicon in absorbing more of the energy, in capturing more of the energy, using what you call the PERC cell in order to design the back nanoscale structure for maximum efficiency associated with being able to absorb all of the energy that hits your solar cell. If we look at the last complete year that was not COVID affected with new energy deployments, 55% of new energy deployments worldwide was associated with solar PV, 32% with onshore wind, 10% with offshore wind. So what this shows is that the world is moving towards these renewable energies, not because someone says they should do it. It's simply an economic argument now. And you need to have free economy in order to allow these to happen, simply because even in terms of volume, what you see is that the larger the volume, the lower the price gets. As a result of the work that we are doing on solar energy, we also did some work to show the government of business, energy and industrial strategy in the UK what the cost reductions are. And for the first time last year, BEIS accepted and acknowledged the fact that large-scale solar and onshore wind is the cheapest form of energy. So although there is Hinkley Point C, which is set to buy electricity based on nuclear at 92 pounds per megawatt hour, solar at present can deliver that at less than 30. So as a result, there is a major shift in thinking and planning going forward, but that will have to be accompanied by being able to have novel storage solutions in order to store your energy, as well as having smart grids and moving away from a single grid connected system to a much more smarter, localized grid distribution in local areas. We've also shown some of the learning curves associated with solar cost and done some training algorithms to show how the cost keeps decreasing. And all these graphs show is the levelized cost of electricity going down according to the world statistics, going down based on the installed capacity, and how there could be an apparent log linear relationship between the levelized cost of electricity and the installed capacity. And this we can predict for the UK will go down to about 3 to 4 pence in the coming years. As a result of much of the work that is being done within the UK to show the impact of renewable energy into the national grid system, there have been a number of parliamentary acts and strategy documents that have been put in place. And within the last 3 to 4 years, there has been major change in policy, with the last coming out last year in the 10-point plan that gives renewable energy a major boost. Furthermore, there are new interconnects being connected so that we can get hydroelectricity from Norway, so direct electricity lines to use the hydro capability in order to stop brownouts. And in terms of costing worldwide, you can see in Los Angeles, 2 cents per kilowatt hour, Portuguese government, 1.3 cents per kilowatt hour, Saudi Arabia, as I said, 1 pence per kilowatt hour, and Sao Paulo, 1.5 pence per kilowatt hour. These are all happening worldwide, and it's something that we can't afford to miss. Looking at Sri Lanka and seeing whether Sri Lanka also has that capacity to take advantage of this particular situation, one can very easily start looking at the possibility, and this is not with huge amounts of research, etc., but just a cursory look. We can start looking at the solar irradiance or insolation, and we can also look at population maps. And what you immediately notice that there is a lot of solar irradiance that we can take into account, particularly in areas where you have large populations. And this can certainly start impacting. And when I looked at things about 5 years ago, typically speaking, the country had around 50% renewables, simply because you already had 40% with hydro. And hydroelectricity is certainly a renewable form of energy. And if you add the new renewables of 11 or 12%, that comes up to your 50%, with thermal coal and thermal oil and gas making up the remainder. If you look at historically, you can see that the domestic, industrial, and commercial activities have effectively shared the different amounts of electrical use. And looking at the UNDP report that came out recently, asking and showing that Sri Lanka can reach its 50% or 100% renewable targets by 2050, it looked at the increase in energy demand per year and indicated that there will be a 6% increase associated with that. Then by simply using global irradiance data, you can map out the space that is needed if you were to look for solar cell-based electrical production. This is purely electricity as opposed to all of the other energy needs. But looking at purely the electricity requirements, what we can do is to say with 14% modular efficiency, he's using amorphous silicon and older silicon grade devices. The black line shows the amount of area that you need in order to meet the electricity demand of the country. If you use typical silicon modules at the moment, which is around 18 to 20%, it's shown in blue here. And just to put things into context, if we take the 2020 number of around 35 square kilometers, that is about half or quarter the size of the Ranawaka Samudra. So effectively, by having solar cells in an area of the size of the Ranawaka Samudra, we can satisfy all of our energy needs for electricity generation. According to the UNDP map, it showed a very rosy picture that by 2030, we would use 25% fossil, which will go down to 10% and go to 5%. So these are proposals that were put in. But you can also start looking at some of the least cost long-term generation plans that were put forward. And this is where I looked at some of the initial numbers that were coming. When I looked at initially some of these numbers in 2015, we had about 1.8 gigawatts of renewable, that's major hydro plus other renewables. And then we had a further 2 gigawatts roughly of thermal and oil and coal systems. So if I were to take roughly, that's 50% of renewables, 50% of fossil fuels. What is slightly worrying is that our energy needs keep going up. Our hydro is pretty much constant. We need to try and increase our renewable energy components if we want to try and keep your 50-50 mark, if that's the objective going forward. But ideally what you want is to move higher than 50% in terms of renewable energy. According to the 2018 plans that were put forward, the new energy mix for the next 20 years indicated again to maintain the parity of the 50-50 roughly associated with activities. But my thought process is that we can do better from a Sri Lankan perspective, and particularly based on the fact that solar energy is now getting cheaper and cheaper year on year. We should be able to try to beat those plans that were put down in 2017-18, where the target was that by 2027, we would have up to 1 gigawatt of rooftop and, 1 gigawatt of ground mounted solar and 300 megawatts of rooftop. Clearly, there are many other plans that have come more recently that I'm aware of that is looking at things. But the problem I'm seeing at present is that it's not moving with the deployment that is needed. Whereas on the other hand, India have moved forward with their Nehru challenge. Looking very simplistically as to what does it take to have up to a gigawatt of energy that is required from solar to add to the current 1.8 gigawatts of renewable energy. What we can do is create solar farms. And this is something I believe the government is very strongly advocating. And if we were to start overlapping the less dense areas with high insulation of solar energy, you could probably select places such as Kilinochchi, Wanakai, Nila Valley, Anuradhapura, etc., to mount roughly 100 megawatt solar farms. And by having it distributed, it allows you to be able to meet the necessary energy challenges. If you look at the peak power supply in 2016, when I looked at it, the peak power supply was about 1.6 gigawatts. By having this extra gigawatt of energy by solar or wind provided, it's possible that we can also make sure there are no brownouts in the country and work with some of the cheapest energy systems available. We already know that there are 100 megawatt plus solar and wind farms being looked at Punarin and in Monaragala. But again, I'm not sure as to how much of that activity has taken place. But what is very important to note is the space that you require to do this sort of increased solar energy activities is not as significant as most people initially considered when they said solar farms will destroy the environment, etc. In terms, if we want to think about space-wise, if we take Sri Lanka space as 65,600 square kilometers, the relative space that is needed is not hugely significant. And we certainly can find the space. And by moving from module efficiencies of 18 to 20%, to 30% efficiency modules, you can certainly reduce that space requirement even further. As indicated earlier, if we take to looking at floating solar, for example, the Ranawaka Samudra has a 91 square kilometers. You could probably get a gigawatt of energy by using just a quarter of that area in terms of space for solar. So this is just an idea that solar can give you the energy that is required. The cost of it is lower than any other fossil fuel around, and it is not going to take up farmland or any other useful land if we were to go down that route. Furthermore, there has been a number of discussions as to the time it takes to build things. Solar and wind are probably the fastest installation and deployment that you can get in any country. In fact, in Australia, you would find Elon Musk challenge the Australian government that within 12 months, he will not just have his solar installations, but also the storage available. And he said he will pay for that if he was not going to be able to deliver. So these are the things that certainly we can look to prepare. In terms of storage, there are a number of options that can be looked at. And in my view, pumped hydro is a very important area that we need to look at. You do not need heads of 100 or 50 meters. The present technology that is available with hydroelectricity can even run efficient systems with 5 to 10 meters as long as there is flow associated with it. And I'll show you some pictures of a project that we are doing in India that emphasize the fact that you can start looking into this sort of activity. So depending on the times that we need in order to fill the potential energy gaps, we can certainly start looking at different types of energy, which needs seconds, minutes, hours, etc., in terms of the storage capacity. So these are engineering problems that there are solutions to, with the cost of storage also coming down very fast at present. I'm working currently with the Smart Cities initiative in the Gujarat and in the Vadodara area. We are looking at a 1 to 2 meter head in being able to generate electricity through flowing water that they have within their various villages within the activity. And what we are looking for is a mixed solar and wind activity, just in order to support some of the other energy infrastructure that is available within the area. I do know that Sri Lanka have many other ideas and plans that have been put forward. In some cases, there are even plans for 80% renewable that is being proposed. And this will cost a lot of money, and certainly it needs to be done with a significant design aspects associated. But from a worldwide point of view, again, looking at it globally, if we want to power the whole of the world with solar, what you see here in these green boxes with a red outline is the total area that I need with 20% efficient solar cells to power the world. So whether we like it or not, the rest of the world will move towards solar and wind as the two main intermittent sources of energy, renewable energy required. In order to be able to balance out the summer and the winter months, there will have to be different forms of storage that comes in, and that storage will certainly become cheaper as we go along. Now, what about the next generation? So I indicated that silicon at the present has got PERC cells that have been improved to a huge degree by nanoscale structuring on the surfaces, anti-reflection coatings, etc. We are also looking to see what could happen beyond that. And in terms of looking beyond that, what we are looking at is the next generation of solar paints. So the idea here is that within your active paint, you would have nanoparticles in there. Those nanoparticles will ensure that the total light that falls in that area will be absorbed. To put things into context, if this is my silicon wafer, the green block here, the thickness of my silicon wafer is typically 300 microns. I can get the same absorptivity associated with the silicon with 100 nanometers of organic inorganic mixtures. So immediately I have reduced 1,000-fold the material I'm using. The silicon was 300 microns. The organic inorganic mix here is 100 nanometers. The organic inorganic mix that we have will be in the form of solutions, and each of those layers will have different properties. One for electrical transport, one for active absorption, another for hole transport, and the final one for electrical conductivity. Using this process, we are working with Europe on a number of projects. We started off on a project called Smartronics that not just looked at these solar cells, but also built large area roll-to-roll manufacturing systems in order to make solar cells on organics. And now we are going in creating an open market within Europe in Cornet and another newest grant that we got called Music Code to be able to produce this in large quantities. So at present, these cells can be bought for select customers, but it's still not mainstream. Within the next 2 years, it's highly likely these cells will come mainstream. And with the work that is happening most recently in materials such as perovskites, we can push the solar cell efficiency on materials such as silicon up to 30% by having what you call tandem solar cells. And those tandem solar cells are going to be so much more cheaper in terms of manufacture and efficiency, that not only get reduced in cost because of the new techniques and materials being used, but also the bulk manufacturing that will drop the cost associated with it. So let me end this talk by emphasizing what I've tried to do is to show the importance of using science and technology, in particular nanoscale structuring, in order to solve some of the biggest problems we have, and energy is probably the largest problem. Energy security to a country can give it huge benefits, and that is something that we need to all try to do in order to get that for Sri Lanka. Sustainability needs to be done so that we do not change our planet and use the needs of future generations. The UN development goals, within its 17 goals, encompasses these sort of developments that need to take place. And from a Sri Lankan point of view, I'm very, very determined that we make sure the heritage that we have, not just the cultural heritage, but also the environmental heritage that we have, is given to our future generations, so they can not only enjoy free water and air, but free light that gives them the energy, so that we can call free energy also being part and parcel of that mix. So with that, I conclude to say that the sun is the source of nearly all forms of energy that is currently being used. It really does allow us to have a higher quality of life, and there's a direct correlation between energy use per capita and quality of life. At present, 80% of the world energy comes from fossil fuels. Unfortunately, the CO2 and greenhouse gases poison the climate that we have. We need to reduce that. We need to move towards a net carbon zero activity. And I want us, as in Sri Lanka, to consider light as part of our heritage, so that we can have solar energy, hopefully for free beyond 2035 moving forward. So with that, I thank you very much for your attention and look forward to answering any questions that you may have. Thank you very much.